For internet, okay, cool. Oh, jeez. Okay, we're almost there.
Is this
Thank you. Okay. Fun. I may have a solution to us not having whiteboards. Someone told me that if you use like alcohol solution on this, it rubs off the like actual the layer, and then when people draw on it, it's just like impossible to erase. That's not right. That's not what I want. It's a joke. Come on. This is, yeah. This should work, but it is not. Why are you not working? This is connected to the internet now, I think. Through my hotspot. Yeah. Connected to my hotspot. And then this should be receiving it.
Is that also connected to hotspot? Is it there?
No, this is my home computer.
Doesn't have to be. Not have to
No,
be the same
it doesn't
one,
have to be, no. I tested this already. I go back in here and we go boop. Share my screen. Yes. Okay, well that was a waste.
Maybe next time.
No, I just don't have time to fuck around with this thing. The thing is, like, I should be able to just open this, and it should at least show that as well. Do you reckon? I'll just try this one thing. Just go back and double check it. Is it? Nope, it's not there. Fine. I'll just use paint, whatever. Hello, everybody. I tried to find something to solve the whiteboard thing, and it hasn't been working. So sorry that we're starting a little bit late, but it just happens. That's just what happens, unfortunately. IT's just become quite complicated with with all of the security stuff that gets layered on now. Like it's almost impossible for me to just do my own thing, but whatever. Um, so last week there was some questions that came to me via Danielle that people were asking. They weren't quite clear on the brief. Various questions about deliverables, and I said this to a few groups, and I'll say it again just to everyone. If you number one, we have to follow the format that the whole course is following. So these are interim presentations. I believe there are boards that need to be submitted, but as well if there needs to be digital media associated with that, which quite possibly everything that everyone's working on here could have, then we've got those floating, those easel screens are in the studio, so we can definitely use those during the presentation. So, but primarily try and have your physical boards. I think it's 2 A1s. On the content of which is up to you. We're designing a stair, whilst other people are designing, towns or heritage interventions and whatnot. In this case, you should have a fairly good idea of what you need to put together to communicate your design. And the critical thing here is that you're presenting a design of a stair and not necessarily a stair, right? So that a design of a stair is far more amorphous and than what the actual artifact is that you're trying to represent. So we are talking about telling a story about how you got to that stair, how you got to that design. There could be options or multiple designs that need to be talked about to get your ideas across. You can look at precedents as long as you reference them. You do not that is not plagiarism. So precedents, references, all of those types of things. So, and those references don't necessarily need to be real world. They could be fictional. You can think of that as real world examples of art rather than a real piece of architecture. You will frequently see art, and like what we saw in the lecture today, you can even bring in a tree branch, and if that's relevant to you, right? So it doesn't have to be a prescribed thing. That is useful way of communicating. It's actually really efficient way of communicating because all you've got to do is find the thing and slap it on. So that's quite useful. But even the drawings and sketches that you're putting in notebooks right now can be useful means of communicating your design for that final outcome. Okay? So if you don't think you need plans, you don't need to give me plans. Okay? If you think you need 5 sections and a bunch of details and a render and maybe a video, great. I'm going to be assessing your design based on what you give me. One thing I've noticed when I was a student was that tutors and course coordinators would give me requirements for output, like deliverables, because that's how they can actually understand architecture. I think that is an important skill to have, to be able to communicate based on your audience. Your audience demands sections and plans, then you give them sections and plans. But I'm versatile enough that I think I can get it. I've worked with people who cannot look at a 3D image, like a perspective, and know that they're looking at a piece of architecture. They're like, this is not how I interface with art design and architecture. I need orthographic projections, like plans and sections, th- get this get this rubbish away. I'm like, but this is the final. This is actually like what's going to get built. No one will ever really experience our building as a plan or a section, but that's just not how that their brain works. Okay, so I'm I'm capable of looking at perspective images and renders, and I don't really care too much about scale in those, as long as you have references to scale in them. So, what's the most important thing that we can put in a model or an image that gives us a sense of scale? Humans, yeah, people. Yeah, trees are trees can be good, but they change in size. Like you can scale a tree up. I can't really tell by looking at a tree if it's an adult or if it's adolescent or whatever. But I can, like, if you put a bunch of adults in, I know what I'm looking at, right? So um, that's now you know me as an audience, right? So you can give me whatever and be experimental, okay? Because the second point I want to reiterate, and I think I've said it, but I'll say it again, and maybe I need to say it each week because there is a slight indoctrination at university, and I would like to break that a little bit. If you fail, do not stress. If the thing that you're trying to do doesn't work, do not stress. You just because your script or your design failed doesn't mean you're failing. Okay? And you should present that and present it in a way that proves that you've learned something. Okay? So if in the final hours of the day before the thing's due, and I know how you guys are going to work, right? And you're stressing out, and your group mates going, this is fucked. Like the script's broken, something's broken, and we can't work it out, and we don't have time to contact Andrew with an email, like because I'm asleep. So like that's that. Like we're not gonna be able to fix anything. Then the last thing you should do is try and patch it up and um, present something that you think will get a good mark, or at least like let's just cut corners and get something in that looks okay. I would much rather you give me the spaghetti mess or whatever you got and say, okay, this is our outcome. This is what we're trying to achieve. This is where it fell apart. This is what we've learnt, and this is how we can do things better. Because this environment is one where I can say, great, you've satisfied the conditions, you get a mark, right? If you were doing that in a job environment, that's when you get fired, right? Not you as a person, probably the company, like that you lose your client. They go, this is bullshit, right? So we're in a safe environment here. Unfortunately, it's not like in your minds. I see, and I'm not talking about you in particular, but the way I've seen students act in the past, they don't treat it as a safe environment, right? They're terrified of getting anything other than a HD. You guys, you guys are constantly playing every game you can to try and get ahead. So some studios feel competitive. This is not competitive. I want you guys to share what you're learning with others. If you think that what you're doing is useful for someone else, let them know, and vice versa. Ask. Don't be embarrassed to ask. Wow, that's really cool. How did you do that? Because that type of environment makes everyone better at the end of the day. This cohort as a group, if you guys come out of uni as a strong cohort, that is better for you to find jobs as well. Like, I saw some work from from Johanna, right? And it looked great, and we hired her. And I'm talking about how amazing like the cohort from Sydney Uni were that year. It boosts all your reputation, right? So, and I don't know if you guys are competitive. I can't tell. Doesn't seem like it. But that's another thing I'd like to discourage is that competitiveness. But let's be competitive with those other groups, okay? What else? Yeah, so you don't get a good mark because you're the best in the group, right? Like I'm not gonna take the best person and go, okay, they're the HD, therefore this person here that isn't the best is gonna get an F, right? That's not gonna happen. And I I really want to encourage you guys to explore. So the whole reason why I've been telling you, explaining how to use Grasshopper via that ribbon, via talking about like how it categorizes things and organizes things, is so that it's better for you to go explore. So it's unlikely that you're going to use all the tools that I've given you because all you're going to get is a bunch of like a line right now, like to design a stair. That's not what we want. But I've noticed a lot of people, the way they're working is and so what we're going to do is we're going to change up. I'm going to change up my curriculum a little bit and show you guys how to do some stuff in Grasshopper today that will probably satisfy the majority of the people in this room. At least what it will do is you'll start to be able to get an outcome out of Grasshopper that is looking a lot like what your sketchbook is showing or what your Rhino model might be showing. Because a few people here, I've seen Rhino models, I've seen sketches, and they're great. And there's no way we're gonna write pure 100% Grasshopper script that is going to produce that because like I would struggle to do that in the time that yeah, no, I wouldn't. But like for beginners, you definitely would. But that's the other thing. You do not. This does not have to be a pure coding exercise. Okay, there is no way you guys are going to be able to produce master's level quality designs with Grasshopper. Like I really like from your perspective, from a designer perspective, I see you guys as being first years as designers in that program, right? Because it's so unnatural to what you guys do. My philosophy when it comes to design and design process has been a controversial one, and I'm constantly arguing with people about it. I went to Arcadia. So Arcadia stands for the American Computer Aided Architectural Design Conference. I went to Arcadia a few years ago. It was in Mexico, so it was the North American, and they had a whole bunch of prominent Mexican architects and academics, and a bunch of American ones as well, in a panel. And I thought I was going to the big league of computational design conferences. It's the big one, right? It's the one where Zaha Hadid and Philippe Bloch and all the mega firms that do interesting things, they present their work at this conference. And this particular conference, the keynote speech devolved into the argument of the pen versus the computer, which I had been experiencing my whole architectural career. It was something my tutors sort of put to me when I was at uni. I had to argue for my marks. Like when I was at uni, I had to be like, I had to say the reason why I used a computer, and this was only like 12, 15 years ago. So like computers have been around for ages. I was up against people that hated the idea of using computers in architecture. I know that doesn't exist at this uni, so don't worry about it. But that rhetoric was still being talked about by the actual people that cared so much about doing computer-driven design, computational design, we were still listening to people argue, what have we lost? And I've come up with this theory that people design using tools and in the environment that they're most comfortable with, right? So the common trend in those people that are so against using a computer for design, rather than using a pen and paper for design, is that they are so familiar with it. They are above the age of 40. All of them are above the age of 40. So they've all started their design careers only using pencils and paper. Not a single one of them grew up with a computer as a kid. Everyone here, like even maybe people that are like my age,
Probably older than you.
Yeah.
I did my undergrad here almost no computers.
Yeah, 15 years ago, right? So you're doing your masters now.
Had a giant break and now I'm like,
Yeah.
give me the computers.
So probably one person, one or two people in this class didn't grow up with computers. Everyone else grew up with probably smartphones around them, right? Yeah. So things have changed a lot. Most of you have played 3D video games, whilst there are some people who grew up with only Pong. So the way that you guys understand 3D space on a screen and how you interact with that screen, be it a mouse or a tablet or with a touch, it's very different, right? But that being said, you've also all grown up probably holding crayons and pencils. And one of the big reasons why you're even here now is because you got through a bachelor degree, and that very much requires hand drawing skills. So what I don't want to do is say, do things my way, okay? What I want you to be hearing me say is do things your way. Refine your process, because that's how you will produce better designs. If you can't design naturally with a computer, fine. There's only one way to get better at that, and that's by practice. But that's not finding those things natural. You have to start somewhere. So we're starting now. The best time to plant a tree was 30 years ago. The second best time to plant a tree is now. So that's what we're doing, right? But I don't want to get in your way, right? Cherry pick what you want out of this course and use it and move forward with it. Don't see this as me preaching pure computer use, because it's not what I believe. Okay, cool. Do I need to say that every week or not? No, okay, cool. Okay. Now, I want to talk today a little bit about objects, or what the way computers think about objects. I also want to talk about topologies. You guys have probably never really had any conversation about topologies or anything like that, right? No. Okay. You're probably better off with topography than topology. Right. Okay. So, in a computer, we are commonly looking at software that thinks of things as objects, in quotes, objects. And the programs we use are mainly working in this thing called object-oriented programming. So what happens is the computer defines this thing, which is an object class, and we can think of that as like a typology or a topology of a particular thing. So Grasshopper, you've already started working with different object classes. Last week when we looked at the type hints for Python, and there was this big list of type hints, and we were saying, hey, Python, we want you, when this comes in, we want you to think of this thing as a curve. That's us seeing into the window of the computer thinking of things as these objects with specific object classes. So in Rhino, the software developers have said points, they are a specific object class. Vectors are a specific object class. And there are various other types. So, and they're very much relating to geometry. So you've got, your points, your curves or lines, and then what we call surfaces. And then I think in a more advanced version of a surface is polysurface, so surfaces that are connected to each other. Grasshopper regularly refers to that as a boundary representation or a B-rep. I don't know why they've changed the syntax of that, but Rhino, that's usually called a polysurface. In Grasshopper, that's a B-rep. And then that can also advance into solids. And then we'll just cover some of the main ones because there's a lot. What does it look like I've drawn there? It's also a surface, but it's a different type of surface. A mesh? Yeah, so a mesh. And then there's these fairly new types of objects that have appeared in Rhino recently. I don't know how to draw them representationally, but I'll try. There's these sub-D surfaces, which are like a mix between meshes and NURB surfaces. So I guess the key point here is that each of these objects are an object class. Each of these types of objects are an object class in programs, but they also have this thing called a topology, and the topology is really getting into the nuts and bolts of parametricism. The topology that I want to play around with today relates to surfaces and B-reps, and we'll sort of talk about why we get into that. So a surface, here, let's just do this. It's just so much easier if I had this. I'll get it to work eventually. By the time that we don't need it, it will probably work. Okay. So NURB surfaces are based on mathematics, and this, like, you guys have already seen some maths here, right? Like, we've talked about Boolean and or functions. We've looked at patterns, all really like base form mathematics, but and we've been talking about geometry. A NURB surface is made up of NURBS curves. You guys have played around with NURBS curves in Rhino. Whenever you draw a spline of any kind, like a curvy line in Rhino, you are playing around with the mathematics of that curve in space, and it's producing the resulting outcome. And it really depends on how many control points you have and the degree of the curve that determines the outcome. A surface is just a series of those curves, and it's usually in a network. Not usually, it's always in a network. So if I've got, curve A, curve B, curve C, and curve D, then as I produce, a slightly more varied curve to curve A, then we're going to see an interoperable connection between A and B, right? I'm saying the wrong word. It's It's on the tip of my tongue and I can't say it. My brain is blocking it out, but you know what I'm talking about, right? What am I trying to say? I'm trying to say. Hang on. Maybe it's easier if I do this. Let's actually make these curves. Interpolate. Thank you, brain. Thank you, brain. It's come back to me. Okay, so we get an interpolated relationship between those. See this little grid. It's probably annoyed you in the past. Like, oh, why has my Rhino model got this? And then you've finally worked out, hey, you could go up and turn off ISO curves. Where is it? Surface ISO curves. Turn them off. Great. That's what I want, right? This guy here, the little ISO curves, these are great because what they do is they actually demonstrate to us how the surface is interpolating the curves that make up that surface. And as I change that particular curve, you'll see it is affecting that particular direction in the surface. Okay. The critical thing I want to get to here is that surfaces, no matter how many edges they have, are always four-sided. They are always going to be made up of this mathematical formula which looks at the x direction and the y direction, or quite commonly it's referred to as u. That looks like a v. It's going to get confusing. U or v. Because you are going to have a series of curves that define the curvature of that surface in one direction, so the u, and another series of curves that define it in the v direction, and it is constantly going to have that relationship. There isn't a third dimension to the surface, and so if I have two dimensions, then I'm going to have the start and end of that dimension. So start and end, we end up with 4, always 4. You can never have a surface that doesn't have 4 sides. I think you guys can all think of surfaces that have more than 4 sides or less than, but I'll prove to you that they don't. They have 4 sides. So here's one. That's a surface that has more than 4 sides. But do you notice something about the isocurves on that? How many are there? 2, right? Which infers, so the isocurves infer the axes of the surface. So how many axes does this surface have? 2, right? So if you have 2 axes, there has to be a start and end of each axis, which means there are four edges to that. And so if I actually bring up the fundamental surface of that particular shape, if I untrim it, look, we've got a 4-sided surface. So that's just so all I did when I made a surface out of that particular shape with the planar surface from planar curves, all it's doing is it's putting down a planar surface with a bit like that bounds that particular object, and then it trims it, right? So it's always 4-sided. Can anyone think of another 4-sided surface? I mean, a surface that they think might not have 4 sides. And there's probably only one more. So we've gone more than 4 sides. So can we have a surface with less than 4 sides? Huh? A triangle? Yeah, let's draw one. And I've drawn this a specific way. I think that's not the right way to draw it. it knows that I'm trying to trick it. Okay, great. There's a triangle. How many, it's got 3 sides. It's got 2 axes, right? You can see those isocurves. So how many sides does it have? 4. Okay, where's the 4th side? It's this point here, right? That side exists, it's just infinitely small. Okay? We actually deal with this type of abstraction of form quite often, almost every day. I reckon probably you guys deal with it every week. And it is via, at least every week, and it is via maps. Here is a map of Earth. And it's not going to let me zoom out any further. Why? Okay, fine. Why? That's so strange. Why won't it let me zoom out more? That's weird. Okay, we'll go to this website. This is one of my favorite websites. I love this website. Okay, this thing's gonna let me zoom out. Okay, cool. This is a flat representation of Earth, and Earth is a sphere, right? So how many sides does Earth have in a surface? If I drew Earth as a surface, how many sides does it have? Who said 4? Good. Yes, it's got 4 sides, right? Realistically, it doesn't, because, like, you can think of, if we think of a sphere in object-oriented coding or in mathematical terms as something that is just a sphere, that is a point, it's got a point that defines its center and it has a radius, then yeah, it doesn't have 4 sides. But if we think of it as a map, if we think of it as a surface, then it has 4 sides, right? It has 2 sides that are exactly on top of each other, right? And, we'll say that that's that line there. So this is both the U side at the origin and the U side at the end, and it loops. But then as we get to the latitude and longitude points at the poles, the surface becomes infinitely small. It becomes, in the Rhino environment, they call it a singularity, but it's a edge that is infinitesimally small. It's 0 long. What that means is, when we look at a web Mercator, so this is called, this projection, this way of unwrapping the Earth is called Mercator, and it's on the web. As we look at a Mercator projection of that surface being pulled out to be flat, as you tend towards the poles, the dimensions get worse and worse. They become more and more unrealistic. So some of the most realistic dimensions for distances on a map like this occur at the equator. So if I grab, like, Singapore's going to be tiny. Let's grab Malaysia. So there's Malaysia. As I pull Malaysia up, if it was on the sphere, if it was closer and closer to that pole, it stretches out. It becomes absolutely huge, right? And the thing is, if we actually drag it to the pole, and these maps don't actually show the pole, because if we get to the pole, it becomes infinite, right? We're actually dividing by 0 there, and it becomes so big that a computer can't even represent it. So Greenland looks humongous, but guess what? It's not so big. Okay? And that giant Antarctica. Antarctica's quite big, but that humongous strip of Antarctica at the bottom, that's just a little cap that sits at the bottom of Earth. Okay, I think people are just having fun. Like, am I just breaking? I'm just breaking people's brains about the maps. Okay, cool. The point I'm trying to get at is that we have these things that have a topology. So a four-sided surface means every surface has that same base topology. When you're always drawing a surface, you are always drawing a four-sided object. And that is going, like, if you start thinking that way when you draw it, you're like, okay, I'm drawing a five-sided surface, but its core fundamental structure is four-sided, then you can start to actually solve that complex problem. So just be aware of that. But the cool thing here is, and we're seeing this on Earth, you can start thinking about 3D problems in 2D, right? This is a map of Earth, which is 3D, and it's very hard to potentially draw these complex things in 3D, but we can draw them very easily in 2D. So you can draw, we can draw a new country, let's call it Atlantis, put it somewhere in the, Atlantic Ocean. Actually, ironically, we'll put it in the Pacific Ocean, right? We can then map that onto a 3D surface by using the coordinates relating to it. Okay? So right now, if you map something on Earth, we use latitude and longitude, because latitude and longitude is a measurement, of angle on a sphere, but it is being converted to x and y coordinates on this screen. So why am I getting at this? What we'll do is we will take the curve that we drew last week, and we will map it onto a three-dimensional surface that we draw this week. So that's one thing we're going to do. And the next thing we're going to do is rather than thinking about this mapping between topologies from surface to surface, so from 2-dimension to 2-dimension, so UV is still 2-dimensional, right? Even though it's on a curved surface, it's still 2-dimensional. We can also start looking at mapping things from a solid to a solid. So taking a 3D object, putting a bounding box around it, giving that a relative coordinate space, and then morphing it into another coordinate space, which I think will very much tie into what you guys are doing, where it seems like a lot of you are designing treads. Here's my tread design, so you can design a tread in origin space, and then have Grasshopper take that tread and put it where you need it to in 3D space, in morph space, right? So it could stretch and pull it as you need it to get you to give you a rough idea of what you're designing. Cool? I think people are still stuck on the fact that Greenland's tiny. Okay. Well, look. I think the Russia's is Russia the largest country on Earth at the moment? Russia's quite large, but it gets a little bit smaller when you pull it down. You get China. China's quite big as well. So yeah, you if you're going to compare these things in that environment, you need to compare them in the same coordinate system, or those things don't work. In a few more weeks, I'll teach you guys about this thing called the geographic datum of Australia, which will be useful to know when you get a job as an architect. Not very many people are taught about it for some reason. But I'll explain it, and hopefully it will make sense, and it'll make your lives easier going forward. Okay. So Let's open up Grasshopper. Oh, I can turn off my hotspot now. Okay, let's go. Did that make sense? Cool, good. I might actually have the script. I might have saved the script from last week. Let's find out. Otherwise, I'll just write it again. There we go. Okay, we don't want that one. The stair one. We want the stair one. Okay. So I have my stair from last week. We were drawing that stair in 3D, right? Like we were drawing it using the X and Z coordinates. But just to make this super, like even though we can technically draw something in 3D, as in using X and Z, we can use that. A lot of people, when they think of 2D, they think in X and Y, right? Like plan. When I say 2D, the first thing you think of is plan, right? That's your go-to. So we'll just stick to 2D for now, and stick to XY. So I'm just going to modify this script so that it uses Y instead of Z. So that all that really means is I'm going to swap out anything that refers to Z to Y. Actually, I feel like all of you are probably frantically trying to copy this. So what I did was I moved this guy to there, and I've added this. Get rid of this and get a unit Y and just connect the output of that to there and there. And my sunglasses needs to be set to that. Cool. People getting the video recordings, right? Okay, good. I see people taking photos of the screen. I'm like, it'll be on the video, huh?
I'm blind.
You're blind. Oh, you're zooming in.
Yes.
Okay, I get it. So many people need glasses. Okay, you guys should be done with that by now. So what we're going to do is we're going to draw a curve in Rhino. We're going to grab that curve in Grasshopper, and we are going to turn that curve into a surface, and the super easy way of doing that is extruding it. So I'm going to grab an extrude and a unit Z, and we're going to put a number slider into that. Jeez. Okay, this is... We are not working in any reasonable unit, but whatever. This makes sense, right? It doesn't matter. It doesn't matter that I'm not working in like millimeters or meters or anything, right? Cool. Okay, cool. And mate, this is concepts. It's not units. Don't matter right now. I'll do one more thing. I'm going to grab this evaluate surface, and you can see my little UV thing starting to show up, right? Want that input there wants a UV. It's not sunscreen rating. It's coordinate. And to demonstrate what I'm talking about, I'm going to use this almost useless slider, the MD slider. This is kind of like a number slider, except it's got 2 dimensions to it. And the output that it produces is a point. Points in Grasshopper are 3-dimensional. They can't be anything other than 3-dimensional. So what this does is it just spits out a point where the third dimension is 0, right? So even though we're doing 2-dimensional output, it's producing a 3D point here, and that's also what this thing's looking for. It's looking for a 3D point. The MD slider, if you double click it, you can control the minimum and maximum value of it, similar to the minimum maximum value of a slider. In this case, we wanted to keep it as a default, so it goes from 0, 0 in the bottom left corner to 1, 1 in the top right. And if I plug that into my evaluate surface, you can see I can move that slider around, and it moves the coordinate of it moves the point on that surface based on the slider. Cool. Does it look like it is following my instructions? Does it? Like it doesn't look like it's following my instructions, but it is. So what is weird about it? Who said no? Someone in the back said no. You guys are. I love your involvement. It's good. But I heard a no from the back. Maybe I didn't. Okay. What's weird with what I've got? You might not be getting what I get, but I think you probably are getting what I get. Sorry? Okay, that's one. That is one thing. So, right now, do you remember last week? I did something to the curve, so that the curve was being evaluated as if it was a percentage. So when the number that I was putting in was a percentage rather than a distance or a parameter. Do you remember what that was that I did? Right. So because surfaces are made up of curves, they can also be reparameterized. So this surface here can be set to reparameterize, and now rather than my number going from 0 to 1 is now being treated as a percent rather than a distance. Cool. So that's one unusual thing. There's one more thing, and it's more about how we think about surfaces than anything. If I just grab this little handle down here, I can't do that. Will it let me do that? Yeah. If I grab this handle down here and I move the coordinate along the x-axis of the MD slider, how is that moving on the surface? Yeah, it's moving vertically, right? So this is the critical thing. Sliders are going to have surfaces are going to have their own coordinate orientation, right? So the way that we've drawn this extrusion, this line here is the v-axis of the surface, and therefore it relates to the y-axis of this slider rather than the x-axis of the slider. Okay, so there are ways to solve that, and we will solve that here, but that's like we're getting very much into like that the website that I showed you, the one I said was pretty cool. This is kind of looking like that, right? Like I could actually, we could start actually putting a sphere in here and actually putting Earth in using this. I reckon 100's too much. There's a sphere. There's a point on that sphere. I can move that point around, and it's, you can see there as I slide that up and down on the pole of that, it's not actually moving. That pulls it down to the other pole, and then there it is. It's infinitely small down there. It's not making any difference as I change that. And we move around. Cool. Okay. So, because this surface has the topology of a surface, I can draw any other surface, and it will have the same rules applied to it. It'll have a u and a v coordinate system, and so I should be able to take points referenced on that off one surface and move them to the other. Okay, so this guy here, this curve, we can draw a surface underneath that stair curve, which we will do that. Let's just do one like this. Let's just draw a rhino one. And then later we'll make the script a bit better. We'll draw a rhino surface over our curve. So just to avoid any issues, don't modify your stair parameters at the moment, or otherwise this will break. Because like if I change one of these dimensions, like, and it goes off the surface, it'll break. But the point is just leave that alone for now, and we'll sort that out in a second. If I grab my surface, rather than evaluating a coordinate on that surface, we can run a function that returns a point's coordinate on that surface. The function is called surface closest point. What it is looking for is points. So here you can see the points that made up our polyline. If we plug those points into this, and we grab that surface as the reference, it returns the closest point. So this is really useful if I've got a surface and I want to draw a line between a point and that surface that is normal to the surface. So here I'll demonstrate that with this. So this is returning that point on that surface, and as I move the point, it's going to find the closest point, and that closest point will always be normal to the surface. Normal meaning perpendicular to the surface. We can get into normal later. But what it also does is it gives us the UV coordinates of that point. So this is how we can get these stair point coordinates on that surface. And here it's giving it to us in that parameter dimension, right? So we're getting a U value of 2.3 and a V value of 1.87. So if we're going to make this translation between the two surfaces, if we want it to be a percentage-based translation, then we need to also set that surface to be reparametrized. So these are now coming in as percentages rather than distances. And I should be able to use these coordinates to evaluate this surface rather than using the MD slider.
I have a question.
Yes,
How do you get these points on the curve?
these points.
Yeah.
So it's these points that the points that we use to make the polyline. You can also, by the way, you don't have to use those points. Like if you're doing a process where you've drawn, if you want to draw your stair manually, or you've got a Grasshopper script that has produced, something stupid like what I'm doing, then you can, as long as you can break that particular object down to points, which you will always be able to do. You should always be able to take a geometry and break it down into its points. So the way to do that with a curve is using the explode component. That'll give you the vertexes of that particular curve. So that is giving us those points, and we can see those points are now being mapped onto that surface, right?
My question was, how are they getting mapped on this surface?
How? But with this script. So how are they getting mapped? We are getting the point. We're getting the point at a particular coordinate on this surface. What's that point's coordinate? Let's say it's 20. That's 25%, or maybe it's more like 20%, right? Along the U, and it's along the V. It's maybe 25%. Right? And then we've got this other surface, we'll say, which looks like this. And it's coming along and saying, okay, there's 20% along the U, and there's 25% along the V. And so it's got that as its point, right? It's doing that for each of the points. Is that what you were asking?
Yeah, I understood that, but in script,
Yeah. So surface closest point is the component that we're using to get the coordinate of the point on the surface. So this is turning the vertex, the point on the curve, into a coordinate relative to a surface. So that's doing the analysis. And then we are using evaluate surface, which returns a point based on a coordinate on that surface. Do it.
so you've connected the exclusion to you set another point at the above level.
Yeah, so I've either got the stair points connected to a surface closest point, and then I've got a curve that I've drawn in space, extruded it, and then I've got an evaluate surface component there. And you just need to make sure that these, at the moment, the way that I would like to work is with these using a reparameterize, so that we're working with percentages rather than distances. What that means is I should be able to draw a polyline now on that with those points, and we technically get a stair, like a stair curve in 3D, but it's now being controlled. The extent of it is being controlled by the curvature of that surface, right? Yeah.
I got the points, I got the staircase as well as the curve, but why am I getting the where?
So these guys here, you probably start noticing that we're getting this thing here. See these?
Yes,
They don't look like points, right? What, these are planes.
yeah,
Okay, so planes planes are infinitely large mathematical objects that have an origin and two vectors that describe their orientation. The reason, like you can see here, what they do, what they're giving us is the the normal plane at that particular point of the surface. If this surface, hang on, I shouldn't have got rid of my sphere. Let me bring my sphere back. If I use the sphere now to draw this, you can see how the planes are. What they're doing is they're like the 3D tangent of our point at on that particular surface. It matters if you want to use those planes, you're more than welcome to. They're very useful. We'll get into how we can use them later, but that's what they're doing. Does that looks exciting? Is that you just like? I'm just seeing some faces being like, "Whoa!" Okay,
So what's the point
which point? This thing? Don't worry about this. This is me. This is me for demonstration
I'm
point.
just wondering about the actual point in that one though. Like,
This.
yeah.
I'm grabbing a point in. I'm grabbing this point here that I've just drawn in Rhino, and I'm just showing you that. See how I'm using closest point on the surface, so it's picking a point. It's working out where that point is on that surface. So if I move this point, you can see it's working out where the closest point is on that surface, and I'm drawing a line. It's just showing you how
Yeah,
closest
yeah.
point went. But we should have this 3D stair, right? Like, I could do this. I could copy my... Actually, let's offset it. I'm going to offset this. I'm using the through point just so that I can manually pick where I want to offset it to. And I'm also going to set the offset type. It's not going to loose. The difference between a loose offset and a regular offset is that a loose one offsets the control points of that particular curve. So the result is that you get a NURBS curve with the same number of control points at the end, whilst a non-loose offset does a proper dimensional offset. So that's usually the ones that we want to use for architecture, where we want something to offset with a uniform distance. I'm just doing this one because it's clean at the moment, but it's really up to you how you want to do it. But if I copy this stuff down and reference this other curve, then it's going to map my stair onto that in a similar fashion, and we can do something funky like this. Let's do this. So we can now control our stair with these two curves. Boop. And we can sculpt it to what we want. Where are we? Does that make sense? Making sense? Yeah?
I'm trying to understand how the closest surface closest point works.
How's it working? Like, what do you mean? Like, do you want me to talk about the maths of it, or?
How is it working for this script?
Okay, okay. So surface closest point is typically written to find the closest point on a surface, but it does two things for us. It actually does three things. It finds the closest point. It also gives us the UV coordinate of that point on the surface, right? So that's the main reason why we're using it here, is that we've got these curves on surfaces, so they're already on there. We don't need to find where their closest point is, but rather we're trying to just turn a point from its XY coordinate in Rhino space to a UV coordinate for so that we can translate it from one surface to another. Cool? Okay. Now's the time I walk around and make sure it's not like. Oh, you're trying to draw a line? Oh. Oh, no. You have a look at my line. No, no. Polylines. Yes. Yes. It's working. It is working. Okay. Some of you may be seeing. Some of you may be seeing something like this. So is it Caitlin? Oh no, not Caitlin. Yeah. Carol. I knew it started with a C. So Carol is seeing something that looks like this. I think. Maybe not. Is that what you're seeing, Carol? No. Let me try and explain. In the most simple way possible. Okay. I'm gonna draw a line from the start to the end, and we're going to use this line to try and work out what's going wrong. If we've got something wrong with our script, so I'm going to bring that line that I've just drawn manually into my coordinate system, and we can see that it's going in the wrong direction, right? Like if I want my stair to start on this side and go to that side, it's already starting on the wrong side. So that is one issue with it, but the other is if I quickly just go and put a point in it and crank that point up. So I want to move this point in the Y direction. You can see that's great. That is technically moving in the Y direction of my surface. And I move it down, that's great. And if I move it into the left and right, it's working. If it's not working for you, it may be because your surface, the one that you're mapping from, is is its u and v coordinates are in the opposite direction to what you've got drawn from that extrusion. You know how when I was moving that MD slider, and as I was moving it up and down, the point was moving left and right. So if I just quickly rotate this surface to demonstrate. So if I grab this line again, see as I pull this up and down, that kink is moving forwards and backwards rather than up and down. Here, I'll show you again. So right now I'm moving it down, and rather it's moving like along the curve. So that's because this axis is mapping to this axis on that surface. So one way we can fix this is we could try and redraw the surface, but that could be a lot of work depending on how long it's taking you to draw that surface. It could be a very complex surface. Rather, the really easy way of doing this is to deconstruct your point, and you can reconstruct it by flipping about. Like you can put the y-axis into the x, and you put the x-axis into the y, and so that should give you you should be able to work out the correct orientation system there. You can also, if it's still not working, there could be, like if you want to flip the direction, you can also write a maths function. So it's a simple 1 minus x. So 1 minus x equals y, which basically takes your numbers that go from 0 to 100 and make them go from 100 to 0. Or you could just flip your curves. Carol, did that solve it? Yeah, sure. Oh, yeah, no, that works. That's fine.
Is that from last week's?
Yeah.
Something weird happened.
Yeah, that's the whole reason that's happening is because we've got two curves, and then like shift. So it's putting this there where we're telling you to.
Yeah.
It might not look right, but that's what we're telling you to.
Right.
So look, I'll do it with mine.
So I haven't put the wrong values into
You've done. It looks right. It looks good. Like, look, if I pull this point out, then it's like this is getting stretched to there, right?
Yeah.
So it's really like at the moment the way we've written this script, it's up to these curves to be correct. Like, there's nothing stopping us from doing this at the moment, right?
Right.
Yeah.
The steps seem to be on an angle, some of them. If they start flat, it makes them really hard.
No, I'm pretty sure they're flat. Yeah. Oh, you mean? Oh, yeah, you're right. Oh, yes.
Yeah, I don't know how to use mine.
Oh, it's just
Right.
Right, okay.
So because this surface
Yeah,
has
that's
a
probably not right.
you've given it a skewed environment to measure to, and so that's why it's skewing the results. Yeah. But that's a great mistake, right? I'll be with you in a second.
Okay, so it's fine.
No, it is.
the endpoint should match the endpoint.
So look, this staircase is starting at 0, and it's starting at 0 now, and it's the length of this curve, whatever percentage that is, it's the same as whatever the length of this curve is that percentage. What did you do to make this?
Yeah,
So this reflex.
whenever I look like,
Because you draw it to the remember we weren't using those last two.
yeah. Did you say grasshopper?
Okay, so still doing that. So right, this is your root. This it's like it's going from 0% to 100% here. And this is going from 0 to 100. Right? This is going from 0 to 90. So I feel like yeah. No worries. Whatever. So this guy and then we've got this is pretty much so you should straight up. but it's a loop. So it's this way. A to the next but then as well, strip is we found the memory strip because using that to make yes. Yes. Okay, so right now I think what people are confusing us is that stairs are kind of stairs in both directions. Like if you take a stair and you rotate it, it also looks like a stair, right? So right now, this point that we have is quite far away from that direction. That's quite far away from that direction. And I feel like you really pull this up. But so if you pull that surface, like if you push the through right, just so that this point here is so that changes. What did you just say? Just undo it. So and I do again. So you move it in the extra. That change. So do you maybe need to then you want to do the deconstruct. What's up? So you want to construct. So, you see, I've got a deconstruct and the construct. We're putting the x coordinates of the point into y, and y coordinate to the x. All that's doing is flipping the axis of those values. And then now we show step. So now you can surface measure the x direction. You see it stand on the x direction. Okay. There were a few people who needed help here.
Yeah.
Shall I start? Yeah. You mean it's not following the curve, it's following a straight line? It's because we're using a fully straight line. We'll fix it up. Okay? Hey.
So if I predict this spiral
Yes.
what if I want to say this I can't happen because once is it
Yep, we're about to solve this. We're about to solve both of these problems. Okay, cool. Okay, it's 11 o'clock. Okay. Okay, guys. We want to add more stairs. It seems like people want to add more stairs, right? That's one thing that this script is not allowing for, because at the moment, if I pump up my stairs, what do I get? I'll break it for you, so you don't have to. Boop. We get this kind of mess. Hang on, let's just tidy this back up a bit. So, ooh, this is interesting. Actually, I think I need this. Doop. Nope. Nope. Now I'm confusing myself. So, let's just do this. Cool. Okay, so we want to add more stairs, but when we do, we might end up with this type of situation where I've got this like weird end piece, and like you can see, I've got a whole bunch of points here, and it's because my points are beyond the bounds of the surface that I'm working to. Right? If I have that static surface in Rhino, then that's not going to respond to my dynamic stair. Okay, so typically what I do is if I have this environment that I want to create a bounds within, I use a component called bounding box. It is going to produce a box, which is probably not what we want. but so what we do is we use these points that we're using as the reference. If we plug that into the content list of the bounding box, that to begin with will do nothing, because by default what the bounding box component does is it finds each object in the list and it puts a bounding box around it. Because these are points, they have no bounding box because they're an infinitely small thing. What you need to do is right click this, and rather than having it create a bounding box per object, we want it to create a box per group of objects. So it puts a box around everything. That will bound all your points. The outcome of this is this thing called a flat box. A flat box is not a surface. It's just a box that has one of its coordinates, so x, y, and z. One of them is 0. So the way we need to turn a box into a two-dimensional surface, we are going to break it apart by using the deconstruct box component. That will give you the x, y, and z coordinates of the box. And we might actually use those later, but they'll give you those. It gives them to you in the coordinate space of Rhino. And we can use that to produce a surface, a nice UV surface. And we're going to do that via primitive in surface. We want a plane surface. The plane surface takes a plane, it takes an X and a Y, and that produces, rather than a flat box, a surface. This is now the surface that we can use as our reference surface. And now I can delete that Rhino surface, go away. I can jack up my, or reduce the number of stairs I want, and it's going to fill in that particular surface. So it's now going, no matter what, it's always going to be from 0 to 100. Now, what I said last week with this script, we designed it so that this domain that goes from 0 to whatever, so 0 to 10, would effectively be like, hey, I've got a stair that goes from RL0 to RL10. But now if I change that slider, it's not going to do anything to my 3D stair, because my 3D stair is being defined by that surface. We're going from 0% of that surface to 100% of that surface, and that surface's height is being defined by this number slider. So we've got two contradictory values that are fighting each other once we start talking about percentages. So what I would do in this circumstance is I would plug my number slider here and use that as the control for the extrusion of that surface, the distance of that surface, so that now as I increase and decrease that, it's also increasing and decreasing the height of my 3D stair. Okay, so that's one thing one thing that we were definitely planning. Some of you have also realized that the final stair object is maybe a little clunky. Like, you want a smooth edge to your stair. You don't want this clunkiness. Why do we think we're getting this truncated edge? Like, just remember, the script is doing what we're telling it to do. So why is it producing that straight edge rather than a curved edge? Huh? It's not the closest point. Hang on. It's in there. Yeah?
Has it got something to do with this
Oh.
step or count?
Is it got to do with what?
Has it got something to do with the step or count that we initially initiated?
No. No. If I increase this to 100, it looks like it's smooth. Oops, that's not 100. It looks smooth. It's not. It's going to be made up of straight lines. Come on, what do we think? What is it that makes straight lines in our script? Yeah, polyline. It's because the points that we've taken, we've produced a polyline from them rather than like drawing a curved line, right? And it's actually going to be really hard to make this anything other than a polyline. We're going to have to get into super advanced like scripting tools here if we're going to do it this way. There are other ways of doing it, and that's how I'm going to show you. So if you want this to be a curved line, I'm about to show you how to do that. But it kind of, the whole reason why I taught you this was so that you understood that you can map between a surface to a surface and how to do that raw. So, and I do it so raw normally that I've actually forgotten how to where is it? Where's the component? It's definitely in here. Morph, map to surface. So this component here pretty much does this script here, at least these three, where you can take a curve. So it's not a point, it maps curves. Where's the other? There's no 0.1 space. Surface box, box morph. Yeah, okay. So this takes a curve. The curve that we want to map is this polyline. It wants an origin surface, so the base, and it wants a target surface, so that's one of these extruded curves. And that's pretty much doing the same thing that this is doing, except the resulting curves are going to be on the surface, okay? So if I just bring this back to 10 or 5, let's do it to 5. Is it doing it? Maybe it's not. Maybe I'm wrong. No, I'm wrong. I'm wrong. No, it is doing exactly what... Okay, never mind. It used to do it. So trick number 2 to solve this is you can use this little component here called pull to surface. Where is it? Oh, pull curve. Here you go. You can find it under curve in utilities. Pull curve. You give it your curve. You give it the surface. It will pull that curve onto the surface. And we now have a curvy stair instead of a chunky stair. Cool. Does that answers a few people's questions? Yep. Now, this is not normally how I would design stairs. Stairs are very much about like you want them to be easy to interact with from a human perspective. So like if I had a spiral stair, what I want is a nice uniform perpendicular relationship between one surface and the other. So generally what I do is I have my control surface, which might be the inner surface of the stair. rather than mapping my stair curve from onto both surfaces, instead I prefer, so would say this is one method. A more realistic method is, I'll just pull this down here. Let's just give this, go back to maybe like 20 treads. So I've mapped my stair onto one of those curves, and I've probably put a little bit of rigor into how deep the treads are as well, because of and how high the rises are, because we want real world dimensions where people don't fall downstairs. But we don't need to worry about that at the moment. But let's say we've done that. These points, we want them to be perpendicular as they extend out of that curve, or at least perpendicular to a reasonable extent. So we can use the function like surface closest point. Oops, sorry, lots of copying and pasting. But let's say I've got these two extrusions. If rather than mapping the stair onto both, instead, if I use surface closest point with these points here, it's going to draw a perpendicular line to this other surface. So right now, this is going to be perpendicular at this point. If I draw, I can draw lines between these right now. You can see what I'm talking about. It's not going to get stretched out. It's going to be a perfect, purely perpendicular relationship. It's not perpendicular from this guy though. But then we can use those points and do the exact same pulling here. And we will end up with a different script relationship to this one, right? Because this is going to stretch all the way that other curve, while this one is just purely going to do a perpendicular relationship. So I could technically give this a straight line. And it'll work out those treads based on that straight line. Is that the right thing to do? Probably not. We probably want, in this case for our treads, our base curve to actually be this straight one. So hang on, let's do that. We get a nice uniform stair across that, and we use one of these curves. And we at least get this uniform stair on one side and the curvy relationship to it on the other. It's up to you. I'm just giving you guys some controls there. Does that make sense? Do I need to repeat that?
Yeah.
Okay. So we don't have to draw our curves the same way. All I'm doing here is I'm using another function to draw points in space. So I am taking a curve in space and extruding it. And rather than mapping onto it, we're using the curve closest point. That you can see there is mapping those points. And because of the shape of this curve, the map is actually quite stretchy. So here, I'll just pull that curve in a little bit just to make it a little bit more realistic. So each of these points is mapping onto that surface with this relationship. Oh, it's 3D, that's why. So let's just project that to the C-plane. Cool, okay. Cool. So we can use those points now to produce a polyline. We can pull that polyline. What's that erroring? We can pull that polyline onto the base surface, and we can now loft between them. And what I'm getting at here is that it is really up to you how you want to define the set out of that stair. Okay, but those are some ways of doing it. Another way I typically have to work when we're doing spiral stairs is that we want spiral stairs to be quite pure. Shall we script a spiral stair from scratch? Okay. Spiral stairs usually need to be quite pure because, like this Baroque monstrosity, was when architecture had to be beautiful rather than functional. But if I put this in a museum nowadays, someone's going to fall down it, right? So, and then I'm the one that gets in trouble. So we want to design for accessibility, so that those pure circular stairs are usually the most advanced stair you'll probably ever do. Um, so we'll script one of those. But let's like, you guys are more than welcome to make your stair as crazy as you want. I've seen some crazy ones, and I might get into how you do crazy ones as well, because there is another reason why this script works, but it might not work for what you're trying to do. And then we'll get into mapping in doing box mapping, or just rather than surface mapping. Shall we break for 5 or 10 minutes? Do you guys want to give your brains a break, and people can ask me questions? Okay. Starting a new script. Yeah, certainly I'll probably Cool. Cool. Yeah, so we're just working in. Yeah, you can have a little idea here later. But like, if that's what you're trying to get, that's. It's just to show that you can rather, you can take your base curve, like this curve here, and have it relate to a surface rather than mapping your sphere onto two surfaces. So it's really up to you, it's up to you how you want to do it. So spiral step might help explain, but basically, generally what I do is when I have I actually want the main part, so that's where the tread map or at least the mid probably definitely. So if you could work with it right there, you have your control with the curve, which is this one, and then means that this is and then it's set. But so this this is not right? Because this You're okay? Okay. Yeah, so you want to use that? That's one of the script. Yeah. So see this one here? Like that. That should be. So we if you want to fill the straight one, then you need to flip your okay, now that the straight bit needs to be longer than the curved one. Yes. Yes. Ah. Yes. Do you want to use it with text? What's in the library? Was that lunchbox? Why did you just spend Good. I need to watch my other videos. Right? So you found all my videos. Yeah, so you've been using that for teaching computational science students. Cool. Probably complaining about tutors. Huh? From me? It's not much number, right? Yeah. The thing is, this one, like the name is just like random numbers, right? The name of the video. Yeah, because all I do is I record the class and I just I forget about that. So you can tell me which ones are the good ones, and then just comment on them. Andrew, this is a good one, and then I'll put some effort into making it, like putting names on it. Huh? Is it working? Yay! Okay, that was 20 minutes, but whatever. Have a nice break. How you going, Danny? All right, cool. Spiral stare. Shall we do a spiral stare? Huh? You got PTSD with spiral stairs? Pardon? Yeah. Danny and I have actually recently designed Spiral Stair together for Riverside Theatres. So like in 5 years' time, we'll be able to point at one and be like, look, there's an actual spiral stair that we've designed. Okay, so spiral stair. How are we going to start this thing? We're going to have the origin point of our spiral, right? It's going to be the center point of what the helix sort of runs around, right? We're going to have a point that probably the tread starts offset from that, right? Like it's not going to be, if we have a circle like, can I move this? Cool. If I have my circle like that, then can I erase with this? Nope. Okay, fine. Then we want our tread to be starting from this point, right? We're going to send a line off in a direction which is perpendicular to the circle. Otherwise, we're going to end up with that weird stair that we just made before. Weird, but maybe cool. And then that's effectively going to stop at the second radius, and I don't know how to get paint to draw me a good circle here. No. Come on. Cool. So that's going to stop somewhere. Wherever. We're then going to... We basically have to take that line and start to rotate it around the spiral. Now, that could either be a line or it could be a surface. So we could define this as like the surface of the tread and then rotate that around. So, rotate array. And then that's going to just be a 2D disk. So as we rotate it around, we also want to move it in the Z. The reason this starts to fail, and also the reason why the stairs that we've just drawn kind of don't comply with things like Australian building codes is because we are missing landings, right? Like landings are an inherent part of a stair. Do we want to complicate this with landings? Yeah? Okay, well that changes everything. So eventually we want to put a landing in. So let's put one here. Which completely breaks up the rules of the stair. So when we rotate, every so often we need it eventually to put a landing in. At a certain number of treads or rises, it has to be a landing. So the way that we are going to do that is let's do that by... For now, we'll just cheat a little bit. What I'm going to do is say there's a bunch of treads in here, right? Because to do this perfectly, it will take a bit of time and thought. So rather, when we get to this point when we need a landing, do we just not move these treads up? Is that too abstract? What do you think, Danny? Huh? Okay, no, we're going to do this a different way. So we're not going to rotate this. That is one way to do it, but that's not how we're going to do it. Rather, we're going to build a surface that is going to make our treads. So imagine this ring is actually a surface, and we are kind of like slicing the surface up at these points, at these curves, and then eventually there are going to be points along that surface where we just slice it up at a longer distance, right? And that can be whatever distance you want the landing to be. So what that means is we need to build these as surfaces that are being rotated in space based on a distance. Then once we have those surfaces, we move them up. So the easiest way to do that is if I have a line like what I was talking about before, this one here, we're going to use the means of creating that, turning that into a surface. Probably the best way of doing that is using a rotational surface. It's what people will do to very quickly draw a vase in Rhino, where you basically have an axis, you have your curve, and then it revolves that curve around that axis, and it produces your vase, right? If we treat this line as the vase line, the profile line, and we treat the center of our spiral as our axis, then we can revolve that curve along to produce that surface, right? The way that is being controlled is using an angle to define the rotation of that. So we'll be controlling the depth of our treads with rotation. It's not the best thing in the world, but we can definitely turn distance into rotation. We can work that out in a little bit. But this is the fundamental thing, how we're going to do that. What that means is you may end up with, in 2D, as these surfaces come along, because this is a spiral, the spiral is going to overlap itself, right? The key thing is that the order in which we draw the surfaces in plan is going to be the order in which they're going to be in height. So all we're going to do is just set a nice uniform spacing height to all of these surfaces, and when it gets to a landing, that's just going to be a landing at a certain height, and that landing is going to be, just a larger tread than a regular tread. Cool. Okay, let's do this. We're going to set this script up without the landings, but we're going to set it up as if there will be landings. Cool? Okay, so things are going to seem a little bit weird or at least if you know Grasshopper a little bit, I might be setting this up in a weird way, but it's purely because we're going to insert landings into this process. So we're going to make a sequence of numbers, but those sequence of numbers is going to be generated without range or series. Okay, let's actually put code to canvas. So we're going to use the origin point of Rhino as our center point of our spiral staircase. And then we are going to use a number slider to define the inner radius of our spiral stair. So in this case, let's actually start working in real dimensions now. So I'll make this so that it can be roughly 5 meters. Boo. So we're going to use the construct point to put a point along the x-axis, and we're going to send a line in the x-axis for a certain length. I'm going to hide my grid because it's kind of getting in the way. So here's our line. And that is what that's going to have the width of our stair. So we can control. I'll just draw a circle in here as well. Boop. That's going to be our inner radius, and our outer radius is going to be this number plus this number. I know I'm going fast, but I'm just drawing some circles, okay? So these circles are purely for as a guide. So we know that line is going between those two. This is very similar to the tree script that we wrote week 1, except now I'm drawing a line from a point in a certain direction and just saying, okay, draw some circles that will represent what that will be when we revolve it. So these circles we're not drawing it from point to point. We're doing it with a direction and a length. We can find the revolve function in freeform surfaces. It is here, revolution. It is going to want a profile, which is going to be this length of our this tread definition line. And then it is also going to require an axis. So we want a Z. We want a line, another line STL. That axis needs to be a line. So we're going to produce an axis from scratch. So we're going to get a line STL. It's going to be based at XYZ origin. So the quick way of doing that, world origins. The quick way of doing that is getting a construct point. That's just going to be at default 0, 0, 0. Plug that in. The direction is going to be in the Z. We don't need to put a value into the L because it's just an axis. And plugging that in, it's going to give us, a CD-ROM because it's giving us a full 360-degree rotation for that particular surface. So the size. This is a this is a full disc donut tread, right? This is one tread. It's just going all the way around, and that tread is being controlled by this domain. And you can see there. Someone mentioned pi earlier. You can see there 0 to 2 times pi. 2 times pi is the equivalent of 360 degrees. So this thing is taking in radians. So this thing is taking a radian, and it's a domain of a radian. So we can grab a construct domain. We used these for ranges before. If we put 2 sliders into that, that is going to determine the start and end of that particular revolution. And that is going to be in radians, okay? So this is in radians. Do you remember how we made it into degrees before? Huh? Sure. We right-click the component and we pick degrees, but degrees aren't there because this particular component doesn't do it. It wants a domain, it's not an angle. So you can find degrees, conversion from degrees to radians and radians to degrees under maths. You can find it under utilities, I believe. Or maybe trigonometry. Yeah, there it is. So there's degrees, there's radians. So if we want to put this in as degrees, we want to convert that to radians. So grab radians. Please don't freeze. Did I? It looks like I've lost internet. Okay. So we can turn these into degrees using this. I mean radians, sorry. You can turn it into radians using this. So I can pull this up. So if I make this 360 degrees, then we can set that to go the full Pokeball, the full 100%. Yeah. Yeah.
I have a problem with my plane. The plane which I'm making is shifting out from the circle.
What's your axis? Is your axis going in the Z?
Yep.
Unit Z with a construct point at the midpoint. Sorry, at the origin point, not the midpoint. Oh. Okay, so this center point, when I drew that center point, I used so it is, you're actually going to put this right. Just have a look, have a look. You were doing it right. I just realized I've done the wrong thing, but whatever. Okay, we're doing this wrong. We are doing this wrong. But we'll get that. We'll get that. I'm just looking ahead. I'm looking into the future, and I'm seeing this going wrong. So we'll do this right. This is how I was planning on doing it until I realized that you guys wanted landings. So this is the way to do it without landings. Okay. The way to do it with landings. What we want to do is we want to produce a curve that we're going to split up. Okay? So this inner circle is in effect the curve that we want to split up. And we want to split it up in dimensions, like even dimensions, and then eventually when we get to the tread part, we're going to split it with a longer dimension, and then we're going to split it up evenly with more dimensions. So I got myself into a bit of a a habit, because this is kind of how you do teach stairs. So what I'm going to do is we're just going to leave this script as it is, and we're going to come down here because this is useful. You've learned how to do a revolution now. At least a geometric one, not a political one or a philosophical one. And instead, we're going to take this point, and rather than revolving it, we are going to rotate it. Okay? The reason we're doing this is that a circle does not satisfy what we want to make a spiral. Because a circle is a curve that goes from one point in the revolution all the way around, and as it gets to the end, it loops back, it connects, and it connects that circle. What we want is a curve that doesn't connect back to itself but keeps going and draws on top of itself and draws a circle over and over again on itself. So the way to do that is to take that point and to rotate it using the rotate transform. We're going to rotate it on the XY plane, the world XY plane, which you can grab here. And really, the only thing that matters for the angle is that we rotate it a lot, just with a large number, so a few times. So we want multiple numbers of rotations, and then we want those numbers to eventually get to whatever the angle we want it to have got to rotating. I'm sounding like I'm having a stroke, but let me demonstrate it. So we want to rotate it, let's say, from 0 to... I'm going to put in 720 for now, but I'll just leave it at 360. We're going to put that into a construct domain, and we're going to put that construct domain into a range. So what's happening is this range is producing 10 numbers or 11 numbers between 0 and 360, right? This is what I meant by we want a lot, because what happens is when we plug that in and set that angle to be degrees, we are going to get a series of points that run along that. If we only have 2, then we're not going to be able to draw the curve properly. Like if I try and draw like an interpolated curve here, it's going to be a straight line. But if as I increase this number, it is going to give our curve some more definition that makes it pretty much a circle, right? So the more points we have, the more circle-like that curve is. We just to demonstrate that this is a spiral, what we'll do is we'll actually transform this. I'm going to move this up I'm going to move it just as much as I'm rotating it. So you can see, oops. You don't have to do this, don't follow this unless you really want to. But you see how that, as I move that up, it's making that a spiral, right? So the idea is that if I go beyond 360 degrees, it's going to spiral further and further up. The more I spiral, the more I will probably need more control points, because you can see here as my spiral gets to be quite extreme that we need more points here so that is still a circle. Okay, so what I'd prefer to do is take this number here, this final number, and divide it by a number rather than just setting a fixed one. So we're going 3,323. For every 20 degrees, we're going to put a point. So that at least gives us like a nice uniform spiral. So now as I pull that up and down, the number of points that are being used to generate that is reducing. And it's maintaining, I think, like a fairly nice looking curve. Cool. But we want this. We don't want it to be 3D. I'm just making it 3D as a demonstration. So what ends up happening is when we make this curve in 2D, it just looks like a circle. But it's a circle that's overlapping itself like 3 or 5 times, or however many times that we've set it to rotate. Does that make sense? Maybe I will keep it 3D just for now, and we'll flatten it right at the end when it matters.
Why don't we divide the curve at the beginning
What?
to get the points on the curve?
Why don't? Huh?
Why don't we divide the curve?
Well, we're making the curve from points. Because if I just draw a circle, it's not going to overlap. So what we're doing is we're tricking the computer into drawing a circle that overlaps itself. Yeah? Cool. We are going to divide this curve rather than dividing a circle. Okay? Is everyone's kind of cool at this point? No, I've got Caitlin's having trouble. Is it? I'll come back. What's up? Why? Huh? Just leave, just let them look at mom. Oh, look. This is the map. It's going from 1076 to 106. Yes. Yeah. This is going to be your spiral. Spiral is like 0 degrees, 20 degrees. It's not like this. This one is spiral. And then this one is spiral. Now it's spiral. This one is worse. We want it to be. Okay, put it back. Sorry. Cool. Guys, if you think you've got something but you can't see it, you can always select it in Grasshopper, hit Control Space, and you can press this little magnifying glass with a red icon, and that'll make Rhino zoom to it. Now, the point at 0. So you're returning at the point, creating a spiral with, yeah, so watch. Yeah? So you're creating a line. Cool. Yeah. Huh? Oh, because what you're doing, they're not repeating, they're rotating. That's these ones, right? So what we're doing, when we're seeing it in 3D, look, as you pull this up and down, it's, this point here is there, and then it's getting rotated there, and so on and so forth. When it goes back to this point, the rotation that we're putting in is so, it's not even enough that the next point is going to be at the same point, it's just slightly further along. So these points here are just slightly further on. It doesn't matter that much. Okay? Cool. By that one, because that's this is a factor of 20 degrees. So that number is quite easily divisible by 20. Yeah, so that's why. Yeah. Yeah, what's up? Yeah, looks right. Looks right to me. Cool. Look, this is the thing. This spiral is not going to control the height of our stair. It's purely there so that we're drawing a circle over and over on top of itself, okay? What's going to control the height of our stair is the tread height that we're going to set later, okay? The riser height, not the tread height. This is so that we can set out our treads and our landings, okay? So I'm gonna pull this back into 2D, okay? I think we should do that. Otherwise, I feel like some people are gonna get a little bit confused. The point is, this thing is actually a spiral. It's just a flat spiral. So we want to start chopping this up into treads and landings, and the way to do that is either via creating a sequence or a range. But the problem with sequences and ranges is that it doesn't give us the ability to insert landings, okay? So the sequence and range that we're going to produce is we're going to set a distance for our tread, like a length, and we're going to repeat that, and then we're eventually going to have a distance for our landing, and then we're going to take that and use that as a pattern to repeat over and over again. So for example, we can have a tread that's usually I like 300 millimeter tread, right? We are going to repeat this number, and a good way to do that is with repeat data. There is also another component. I don't know why these, like, I have, even though I've been using Grasshopper for like 15 to, I think it's almost like 17 years now. Can't be 17 years, 15 years. I've been using Grasshopper for 15 years. I cannot work out like when to use repeat data and when to use duplicate data. But in this case, the only reason I want to show you duplicate data is the comedy that exists in Grasshopper. You guys have probably realized what that is, and I'm not going to say anything more. If you don't like what Grasshopper is doing when it comes to comedy, for example, if you don't like the icon for duplicate data, you can go to File, Preferences, and under Interface, I think it is, there's a content filter. So you can download stuff from the web, and it could have stuff in it that you don't like. So you can set your content filter to be strict or moderate or whatever. The point is, if you drag that there, that'll get rid of any of these little icons that you don't like if you don't like them. Okay? Cool? Huh? You like this icon? You prefer the other one? Okay. I like it too. Okay. It should be It should be the multiply icon, I think. Okay, so we'll use repeat data. Um, how many treads do we want before we have a landing? Yeah, okay. Let's make it 10. That's not necessarily the rule, but let's just make it 10. So we want 10 300s. Cool. How long do we want a landing to be? A meter? Okay, cool. Now, I've got one list and I've got another, and I want them to join. What have I used in the past to join lists? We've used weave, right? Someone asked me about merge before. This is the right time to do merge. Okay? So there's merge. What merge does is it takes lists and it just basically slaps them on top of each other. In this case, this is not doing what I want it to do because of this thing called the tree branches. This is advanced grasshopper. In this case, the way to solve this is by flattening your paths coming in. So if you hit flatten there, that will get rid of that particular problem. Some people say, if in doubt, flatten it out. Okay? Which I completely disagree with because it doesn't necessarily teach you what flattening does, and I'm imagining that's what you're about to ask.
I want to ask, like, what's the difference? Like, what difference does it make to flatten the data coming in as compared to flattening the data coming out?
No different. Same thing. All it's doing is it's destroying that little path up there and setting it to 0. Okay? What it's doing is it's just making sure that these branches have the same address, so that gets repeated there. Not repeated. Gets concatenated or appended in the appropriate way. In some circumstances, flattening is not the right thing to do. I'm saying that now without telling you what flattening does, but just please consider that if your script is not doing what you want it to, it may be because you have flattened rather than done something else. Okay? Cool. So we want that flat, and what that's doing is it's producing a pattern of numbers where we're effectively saying we want to run along this curve and at 300 and then at 300 more and then 300 more and so on and so forth, we're going to take a cut. So how do we get this so that it relates to a dimension along that curve rather than it being like the actual step? So I want this to say 0, 300, 600, 900, 1,200, and so on and so on and so on. It's not multiply because we've got a bunch of numbers. Because if we multiply it, eventually when we get to 10, we need it to multiply in a weird way, right? We need to multiply and then add. So what is multiplication other than just doing lots of additions? Right? It's just a bunch of additions, right? So there are some maths in these operators. There's a bunch of maths functions like addition, multiplication. I think we've used enough of them now for you guys to know that they're there. There is this guy here called mass addition. What that does is if you put a bunch of numbers into it, it gives you the total of all those numbers. Cool? What it also does is tells you how it got to that total. So it gives you the cumulative addition of those numbers. So 300, 600, 900, 1,200, so on and so on and so on.
I have one question not related to this.
Sure.
What's the difference between when you get dash lines and
Okay. The wires in Grasshopper represent how complex the data is inside them. So a basically, how am I going to show this? That is typically what you're going to see. Here we go. So see this wire? That looks different to this one, right? This wire represents one value, right? So we've got 1,000 in there, and that's one. There's only one item in that list. It's one value, not a fixed value, just one value. This one here with the white core means it's more than one value. Okay, and then if you've got a list that has multiple branches in it, and so I'm going to just do that via doing a partition list here. So you can see here these branches.
That happened before you merge the two data.
Yeah, so that's what was happening when I did the merge. Yeah, so here, look. When you've got more than one branch, what happens to that wire, right? It becomes dashed. So when you have more than one branch, you're going to see a dash. Cool. How often do you look at the wires like that? I knew someone who he turned it off. So it's this thing here, draw fancy wires. He turned it off, and like I never look at the wires. I don't think I look at the wires, but whenever I looked at his scripts, I'm like, there's something wrong with your script. I just can't work it out, but I just can't read it. So there is a subliminal thing for me when I look at a script that I must somehow look at these dashes and these lines for me to actually go, okay, I know that there's more than one item in that list, or at least it definitely changes the way that I read the scripts. So that's what those are for. Okay, mass addition. Back to the script. That's adding these up. So this is where we would like our spiral to be cut to make a tread, right? So we're probably missing one. Should we do this with a split or with a domain? Let's just do it with a split. Split? And then get rid of the last one? Yeah, split. Okay. Yeah, might as well. So here we've got shatter. Shatter will take a curve and split it at its parameters. This is where things are going to get a little bit funny. Okay, so my spiral has parameters. The parameters are probably associated with the points that I've drawn. So let's say I drew a point here and I've got a point here. This is probably, like in the way that Grasshopper kind of thinks, this is coordinate 0, and this is coordinate 1, and this will be coordinate 2. So if I've got like 20,000 points, then when I go to put in a parameter, it's going to be relative to that. These numbers are not based on that curve's parameter set, right? It's based on distance. We want to cut the line at a particular distance. So I typically, whenever I do any form of geometric function with curves, I'm usually, even if I'm doing a distance-based one, I will always reparameterize it because the parameters aren't always going to be based on distance. They may be based on how the curve is drawn. So the way that you split it with reparameterize is you need to measure the length of your curve. So we can do that via length. So we grab our curve length up here, which is 53 meters long, right? Much longer than what my stair needs. And then what I want to do is I need to turn my... I've lost internet again, have I? No? Okay. I just need to get I need to turn these dimensions... these dimensions into percentages. So, go back to high school maths. How do I get a percentage? I take the number and divide it by the total. So I take my increments and I divide it by the total length, and I should get percentage values, which we then use to shatter this curve. And we just need to remember that we are shattering that curve with percentages, so we need to reparameterize it. So I'm just going to hide everything while you guys follow along and just show you the first curve that we get is this one here. So that's probably going to be our first tread. Yeah? Yeah, what I'll do is I'll start moving them so that we can actually see what's going on. Okay, you don't need to follow along with this. This is just me showing you guys, what that shatter did. Come on, sorry. See what it's done is it's started to break that up. So, but it's just in 2D, right? That, like, we can, maybe it's even easier. I'm going to show you the start and end of these shattered lines, right? So it's shattered at that point, then this point, and so on and so on and so forth. Yeah? But we're starting to, you can see we're starting to get the beginnings of a spiral stair there, right? Once, like, if I shatter them and then start moving them up incrementally, that's spirally staircase, yeah? What I'll do is I'll just hide. What I need is everyone to get to at least this point. It might not be obvious that it's working, but this is the point that we need it at. I'll hide. Just grab an endpoints and chuck that on there. That's pretty much what we want. Only an hour and a half to go. Pardon? Which way? That way? No, you don't want this. You don't need this. You don't need that. Don't worry about that. That's what we need at the moment.
And that circle is from the first script, isn't it?
Which circle?
The one that shows in right, like you turned off.
Yeah. Here, just go up to that first script and just turn this all off, okay? You don't need that. Cool. I think it feels like everyone, no one's putting their hands up, so I feel like everyone's at this point. Cool. Okay. Now we're going to rely on just quickly. We're going to rely on the way a circle works. So I'm just going to very, very quickly scale my curves. We're going to fix this up later. This is just so that I can get everyone to a point where we can see a 3D stair and we can correct any errors that are in the script. But what we're going to do is we're going to scale and we're going to just set the number for the factor of that scale to be higher than 1. So what that's going to do is draw the it's going to take your curves and scale them out to be, give it some actual dimension to the stair. And then we are going to produce a surface from one curve to the other. This is where things can get a bit advanced. So we're going to do that using this component called ruled surface. This is similar to a loft, except it works like a line, right? In that you've got one curve and another, and you're just saying, I need a surface that goes from one curve to the other. Don't want to get any more advanced than that. So we have our curve, our first curve in the, our first set of curves in A, which is our shaded curves, and our B list of curves, which is our ruled surface. And that should produce a bunch of surfaces for our stair. And then what I'm going to do is exactly what I did down here. So for those of you who were interested in that, we are going to repeat that. We want to move each of these treads up a uniform amount. What component have we used in the past to produce a nice even set of numbers? When I say even, a nice consistent set of numbers that step up the same number each time. We did it last week. Huh? Series, yeah. What did you say? Sequence? Yeah, it's called series, but yeah, it's the same thing. It's under sequence, and we can find series. How many numbers do we want to produce? The number of treads, right? So we want to get the length of the list of treads. So at the moment, I've got 11. We can use list length to measure the length of that. That's going to tell us, it's not 11, it's 12. It's going to tell us there are 12. So we can use that to determine how many numbers are going to be in the series. And what is going to be, these are going to be the heights of our treads. So what tread height would we prefer to use? Yeah, let's use 150. I like it. I like 150. That's a good tread height. Now, where would 150 go? Right? Okay. And then, if we just closely look at this, what's it going to draw? It's going to draw a tread at what height first? And do we draw treads at 0? No. Right, so where else do we want 150 to be plugged in? Right. So it starts at 150 and it goes up by 150. Cool? And we're going to use this to generate a Z vector, which we can use to move our surface. Ta-da! Now, there's something weird about my stair. Okay, hang on. One last thing. I just want to make sure that people have a normal looking spiral stair, and then I'll come around And so we can get everyone to produce a normal looking spiral stair. What's strange about my spiral stair? Yeah, so there's basically, it's got a halo at the top. So you get to the top of the stair and you bump your head on this weird, looping tread. The reason that exists is because we're taking this really long curve that loops around itself and we're splitting it, and then we're splitting it, and then we've got this really long one at the end. So one way that we can just solve that is get rid of the end. And do you remember how to get rid of the end? Cull index. And what is the index of the last item? Yay! Huh? You could do that as well, but -1 is also the right thing. But yeah, you're right. That is another way of doing it. Someone's been learning more about Grasshopper. So we do it. We run a cull index on the last one, and we end up with that spiral stair. If your script is working, great. I'm going to give you a nice little tidbit. You can repeat your data after this merge, and then throw that into a number slider. And I can set that to 100. That's, I think what that's going to do, is it going to do what I want it to? Let's just double check that that's actually doing the right thing. What that's going to do is it's going to run through the data and repeat it. See how it's repeating the 1000 at 10 and the 1000 at 21 and so on and so forth. So when I plug that into the mass addition, that's going to give me the, as I increase that number slider, it starts inserting the landing every 10 treads. Okay. If that's not working for you, put your hand up, and I'm going to come around and fix your problems. Okay. I'm going to leave this up. I'm going to go from the front to back. Okay. Okay, so you need right now you have the surface, but the surface is only going from one curve to another. Can we do this? So we only want to, do you only want this rotation? Do you want rotation to make to right, to the verses? Cool, this is great. And now, so look, if you pull that number slider out, it'll make it stand wider. Cool. And then the last thing is, what I did was put the point back, so if you hold the function, hold the function, drag that out. Okay? That out. Yep. In it, yeah. Now we're going to plug that in. Because what we're doing is we're deleting the last one, and then the indices of that needs to be the last one. What do you want to double click? You can do // -1. Indices. And I would undo what you Oh, you know what? See, this is what I was saying earlier. You can make Grasshopper make really cool looking stuff that isn't right. So are you okay with the Grasshopper in like text mode? Does that work for you, or do you prefer it with the icons or text? It's up to you. Because you mentioned last week you have dyslexia, so okay, you can get that like on the display for icons. Does that help? Okay, you might have to do that every time you start it up on these computers. Okay. Now let's work out what's going on. I'm just starting over a bit because this one's a little involved. Okay, sorry. Okay, so one thing I did, the only reason I made that to the original spiral 3D was so that we could see it. I could show people that it was actually like repeating on itself. We don't want it to be 3D until we turn it into treads. So we need to get rid of that, right? So that's one thing. This looks great, that looks great, that looks great. Okay, so this mass addition is producing a number 3,206, right? What we want is we don't want to split the curve at that coordinate, we want to split it at these increments. So this is the partial results of the mass addition. So this is the equivalent of doing, so you can see that 306 to 900, the equivalent of 300 to 600, so on. So this is the number that we multiply by 1. So what that's doing is it's shadowing this height. So that's producing this surface. There's a lot of surface there, right? That's why you're getting this weird stuff. But the result is this, right? So there's one thread, there's the next, and so on and so forth. There's the landing. And then repeat that, so on and so forth. The thing is, this component is splitting at these dimensions. The curve is longer than the standard program. So there's a spiral. This last spiral is a tread at the moment. So that's coming out of here. We want to get rid of it. We don't want to hide it. Just get rid of it. So it's the last one. So the last one is the last one. So we can use that instead. And now. Yeah, get rid of the thing, get rid of something that is cool. So yeah, and you've done this one, right? So you decrease the increase of that. Adding the traits in. Cool. No worries. Okay, we had I'll get you guys. That looks good. It is going out. It is super good. Was put another big Okay, so guys, I'm seeing a common trend. I got rid of this move at the beginning of the script. We want this to work in 2D until we start moving the treads up. So when you have your rotate, all we want is the rotate going into the interpolate curve, okay? So that's a common thing I've seen, so I'm just saying that now. I have a tendency of like walking away from the script. It definitely will help, okay? It will definitely help. This is really strange. But it's cool. Actually, this is probably okay. So we've got the interpolate curve, measuring the length. Here, this is all right. So these numbers percentages, length, absolutely great. Oh, okay. So you can code the index for the scale. You haven't code the index for the rule size. So see, we want to get that. That's one thing. So what that's leaving us with is bunch of, that's leaving us with these ones. Okay, now, see that on this slider? What's that doing? Yeah, but what have you got plugged into? So you're getting it, you're producing 150 trees. Oh, height with that. See this list length? That's how I had it set up, right? So we want it to start at 150 and to go up by 150, but we only want to produce however number of these we've got. So that will leave us with that. Cool. Now, last thing I grabbed. Let's look at that down for this repeat data. If you have a number slider in that, that's going to repeat the data in this pattern, which is going to give us the ability to produce as well. Yeah? Yay! No worries. Just hide it. It's this. Hey. You scan and then you unzip these cards. Yeah, and then what we want to get rid of this one. Cool. And then have a chat with Isha. Have a chat with Isha to see where she put it. It's going to be I did it with a shadow. I did a shadow. You can do it with that this one, but put in there. Yep, and we want to pick an indices, which is -1. Yeah. Or you can reverse it. Yep. Now we want to plug that into the geometry and the rule surface, the geometry of the scale. Yeah. And also the rule surface. That one, yeah. Yeah. Cool. What? Yeah, what is that? Okay. Was there any questions that were through here? I'm pretty sure there were. This is just the spiral. Okay, so this is right so the size of this is quite small. So all these So that's 2 meters. Oh, that's shattered. That is a little bit. Does everyone want me to incorporate scale as something else? Look, this is this. Go. That looks good. No, but it's working. That's the step.
So I've saved it
The
already.
last one. Okay, so the last one, what I need to do something is
Yeah, so I just drag and drop it.
We're going to get rid of the -1. So at the end of the list, we get the last one is -1. That's the first one. Right? And what's the next one to that? 1. What's the one before 0? -1. So the first index is 0. The last index is -1. Cool? Cool. Okay, that whole index just needs to be negative. Just try it. Oh yeah, I'll put it. I can see what's on. See this? This is a unit. So this is 212 millimeters. That's about that big, right? So what we want. Right? Look, you got some stairs. That's the only thing. Hello. Any of you guys been spoken to? I will eventually, but I'm going to do it a bit back. Okay, so I will get
I was doing screenshots.
So,
And then make
what do you guys? Looks like you're fine. Does this relate to the script?
This, yes.
Okay.
I somehow it's not generating the steps.
That's the only voice rather than
That's why I was.
hello. That looks great. Yeah, you didn't need help.
That's why I was.
Look. This point, that's the start of the stair. So the stair is revolving around this point. It's only like 400 millimeters away from the origin. So it's a very steep spiral. So what we want to do is pull that number up. Right? That's as far as it is. Is there anything else you need to do? Oh, it stops. Okay. So That's going to be determined by this. You want your spiral, the spiral to be larger than you need to right?
Let's just figure it out first. We get
And
like
this
this
seems to be
it's not like
I might just do this. You're just going to that's
I think this is super
okay, what I'm going to really be disappointed is if I get just a spiral stare and these things, okay? This is going to be a stare. Jen's going to look at all those stars and be like, they're all the same. Yeah. Yes. Yeah. Yep. 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 Okay. So these guys have like help. Yeah. Huh? Yeah. Okay. Reprioritize. Reprioritize. Takes put a number in. So for example, if I have a text and I point that curve. Yes, that's it. Oh, that curve is that when it breaks your spiral. Then it's circle it through. Breaking it up to 300, 600, 500. Yeah. So what's the result? So the number that we've chosen, we've made it a set. So it's only going to be like 0. So you've got 30, like 30, and it's like 0, 1. The reason why it's done that is because it's negative 0, and then 0.01, and then 0.02, and so on and so forth. So when you parameterize it, it's going to use a different value. In some cases, it could be distance, like in millimeters.
Yes,
But in other cases, it's the mathematical curve. So your curve has got, like, let's say, 100 points. So if you look at 0 and 1, it's going to divide up the curve from like that many times 0 and 1 in that first point, 0, the first point and the second. So we reparameterize and we save the relational settings so that we can control it set it as okay, I'll come back and explain it later, okay? I will explain it. Okay. Someone else used Russell as a change. Which was great. Okay, but that's changed. Okay, yeah, good. That looks great. That looks like it's that looks like it's fine. That looks good.
No, not this one. I just have a question.
Yeah.
So you mentioned about saving the.
Yeah.
So we just
Yeah, why not? standard. This row looks good. So this is where you can get the clashes, right? I would be very careful. Try it. Try it on a file. Before you try it on something. Okay? Make a grasp of script that you don't care about. Save it. Get creative, work on it. You can work on it at the same time. And try it at the same time as you do it. Okay? You can. If you want me to run it through that, or just look up on, just type into Google how to get an old commute in it'll so everybody just go okay. Good. You go okay. Yeah, right. Yeah, like you feel like the control over it. Cool. Good. Yes. That is the rock. This is the right that the right. So this should only be right there. Right? So now I'm looking at what I can now. And if I go so that's what I'm down. This will start with the reference. As this gets pulled down, it's probably so the reason why it was that when we said 20, this is probably better it's basically so And it sounds way more than
Exactly.
so a good circle, right? How do I decide what unit? This is the starting rotation. This is 0%, right? So you can get around this. So you can understand that circle's rotation. That's one thing. Also, rotation. So someone out there has decided that we're going to, when we say degrees is value when 360 is a whole circle, and therefore 180 is half a circle. So someone out there a long time ago decided that that's what the unit of a degree is, right? You can think of this as how many hours is 360 degrees? Right. So you know that when sometimes when you look at a rotation model and it describes the planet, that's actually that's a rotation. So if we go back to the raw mass of a circle, we get down to this super important value. Right? So we can also understand this rotation as a number related to pi, and it's a magnet that it's 2 times pi radians. So it's just so 2 times pi is a number, and we're saying that from a mathematical perspective, radians actually, radians are more aligned with the way that maths functions work. So if you actually have that's like one way to describe it. It's a way of describing it. That is one way of describing it. So if you try to use that function, actually use maths to get conditions within that environment, you're going to get results that are enhanced. And then we usually use those two degrees because what we don't want is 6.2. Like that shouldn't be what we have to write. And then a lot of people don't understand that because they do. Like 360 is so much things that like even like 5 things, right? So that's why that's it's so like it's no different to feet and buildings, right? Apart from that, yeah. So you do different radians. The thing is a radian, like you roughly around between like roughly around the same radius as a full 360 degree EV check. And that's because that's because what you're doing is you're dividing it in such a like you're watching the around so that what it's doing is it's drawing.
I don't want to go, yeah, look at this.
Cool. Hello.
And like you don't have to just select the banner, you can just find it.
Yeah.
How do we calculate
Okay, guys, we've got two directions that we can go right now. We've got 45 minutes. You can either try and cram 45 minutes if you guys wanting to talk to me about your assignment, which I don't think is probably not a good idea, because there's no way we're going to get through everyone in that amount of time. or I can show you how we can take a model of like a tread, like a fancy looking tread, and we can map it onto the treads that we've just set out in this script. Which one do you want to do?
Second one.
Cool, okay. So, what's next week? Next week's week 4. Then we've got week 4, week 5, week 6. Next week, shall we just focus on your assignment next week? Okay. Okay. If you guys want to make like a quick Rhino model of a tread, if you don't know how to model in Rhino, here you can just do this. If in here, just grab a cylinder.
Should I be in a different file or the
Same one, same one.
Sorry, even the top.
I'm gonna draw a cylinder in the right view. Okay, so you double click here. Okay, see this little cube, dude? You hold down on that, and there's a cylinder function. Just draw a cylinder. So now, once you've drawn the circle, you go out of the right view, and you can set the length of the cylinder. This is going to be a tread, not a very sensible tread. I've modeled this one as well. You know, basically what we're doing is we're going to take something we've modeled, and we're going to move it and stretch it and fill it, like place it into the position where we want our treads. Okay? There's 2 ways that we can do it. And if we use this method, I'll show you the first way with the spiral stair is, see this shatter? Once we get to the cull index, we can create a reference geometry that we can just use to move and rotate our object into that position. So it's a Euclidean move, not an affine. And it would just take out that object and move it. And the way to do that, the best way to do that is using planes. So using this cull index curve, let's just take these curves down here and move them away. I'm trying to do this quickly within the next 40 minutes. So bear with me. I'm not going to skip over anything though. What we are going to do is measure the midpoint of that. Oh, hang on. Before we do that, see this move? Grab that move, and we're going to move these culled indexes by that move. And that's the curve that we're going to use. Sorry. So at least our curves are in 3D. We need to generate a plane. Planes, as I mentioned earlier, there are these infinite things that have an origin point, and they have two vectors that describe how they exist in 3D space. We can generate planes off these curves. This is going to look really weird, by the way, but let's just do it. We're going to generate planes off these curves using this horizontal frame. There are various other ways to generate these planes. So you can see there's a perpendicular one. But in this case, let's just use the horizontal one. And we need to give it a coordinate. In this case, I want it in the middle of the curve. So we're going to set the curve to be reparametrized. And we're going to give that value 0.5, right? 0.5 is halfway between 0 and 1. It's going to give us the midpoint of that curve. Cool. Can we see that plane? Probably not, because it's really small or really big. So planes have a preview plane size, which you can control under display, and they will show at that uniform size across your model. So if your model is a ring, a piece of jewelry, then your planes should be sized appropriately to what you're working on. So in this case, because we're working on a stair, let's set that to 500. So they're 500 millimeter sized planes. Danny knows why this is going to look strange, right? Okay. We want to take our object. In this case, I'm just going to use the cylinder. We'll swap the cylinder out later for whatever you want. So I'm going to bring that in via a geometry component. Let's just say your tread is more than one object. Like it's 2 cylinders. Actually, let's make this slightly more realistic. 2 cylinders like this. What we want to do is we want to somehow turn those into one object, right? Because for every tread, we want those multiple objects to be moved into that position. So Grasshopper lets us do that via one of the transform utilities, which is group. So if you grab a group, that'll turn 2 objects, like 2 reference extrusions, into a group with 2 objects. Do that even if you've got 1 object, okay? Because then at least you can just go grab multiple objects and put them in the one. I'm going to move this relative to the origin point, okay? So this is the origin point of the model, and I want my treads to be related to this plane based on the relationship between these objects and origin. So if I want that to be the top of my tread, I'm going to move my object so that it is it's lower than 0. Cool. Oh, I've lost connection again. And what we're going to do is we're going to use this Euclidean transform called orient. Did we use this before? Did we use this for the trees or did we use something else? No, we didn't use it. Okay. So what orient does is it takes an object, it takes a source plane and a target plane, and it moves that object based on both the plane's origin and its orientation. Okay? So our grouped objects, we want to move them from the world XY plane, and we want to move them to our stairs the curve's horizontal plane. And you can see here that the plane on the stair is pointing a different way. So if I grab those treads and I point them, I think if I point them in the Y direction, okay, I gotta flip them around. Point them down, there we go. There they go. Does that make sense? Okay. Now that might be good enough for you, but it's not good enough for me. Number one, we've got that landing. It doesn't work for the landing, right? One thing that we can do is we can use the pattern system that we used last week. So we have dispatch. If you want, you can dispatch your planes out. So you can say, hey, we have a pattern of tread, 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 landing. Right? So the 10th item, I think it was, yeah, we have 10 treads and then 1 landing. So if you have a pattern, you can say, hey, only do this for the treads. Oops. We need 1 more 0 in there. And then if you wish, you can design a landing and model it, and then use this exact same method to move your landing object into place. Okay? So that's one way of doing it. Just remember, if you modify this Rhino object, so for example, if I stretch it, come on, it's going to filter through onto those objects there. Cool? Okay. Second way of doing this. In transform, there's a whole bunch of methods to do things like, see these mappings. You have these like box mappings, rectangle mappings, and triangle mappings. Box mapping is probably the closest one that we want to what we're doing. What it takes is a base geometry, a target box. A source box and a target box. Is this going to work? Because these aren't boxes; they're surfaces. I think we have to make a box. Surface box. Hang on, let me just test this out and see if it works, because I don't really do this much. This is definitely not something we do regularly. Yeah, we do want this. Okay. Okay, yeah, that works. I think that works. Cool. That doesn't look right, does it? Mm. Yeah, that's what I want. Okay, so this method is going to produce this as an outcome. So you can see what it's doing is it's taking this base geometry that I've drawn here and it's stretching it onto this surface. So it's doing it like a topological transform from one box to another. The way that I'm doing it is that we need to generate a box for one of these as a source. So the transform function that we're using is called boxmorph. Boxmorph wants to take geometry. It needs a reference box and it needs a target box. Boxes have their own object type in Rhino, in Grasshopper. A box is a very special type of object in that there's only a few ways to generate it. Like if I draw if I grab a bunch of surfaces and I join them together that look like a box, it's not a box according to Grasshopper. Boxes can only be generated with very specific functions, one of which is the bounding box, right? So here you can see when I run a bounding box on that group, the output of that is a box. It doesn't say a B-rep, it doesn't closed B-rep or an open B-rep or a surface, it's a box. So that's critical point number one. What this is doing is defining a box that is containing our objects. And the X, Y, and Z of that box are going to end up being the U, V, and the third relative dimension is going to be W. So UVW of our final geometry. So we are going to take our grouped geometry and transform it using this box. And now what we want is a target box. The problem is the target box, we don't want to run that on we don't want to run a bounding box on these surfaces because it's just going to produce a nice, like hang on, I'll show you what it does. It's going to produce a box around each one, and it's going to be relative to this plane, which, so they're all going to be oriented one way. And so if I plug that in, it's going to end up being a bit of a mess. Come on, show me the mess. Yeah, like see how all of these cylinders are kind of flat because we've got a flat bounding box of our surface, and then they're all oriented in the same direction because the bounding box plane is pointing in it's using the XY coordinates to generate itself. So we can't use the bounding box for that. What we want is we want a box that also understands that it's being generated from this complex surface. So what they've done is they've added this special functions in here for us to generate boxes from surfaces. So here, surface box allows us to produce what Grasshopper calls a twisted box from our surface. And that will have all of the instructions in our surface that will morph the object based on how the surface is drawn. So if your surface is exactly what you want, all you have to do is plug that surface into both the S and the D of your surface box. This D is looking for a domain, so it allows you to pick a specific domain of your box. Like you can say from 0% to 25, 0 to 50 or something like that. If you plug your surface into that, it's giving it the instruction, just give me 100% of that surface. Okay? So 0 to 1, 0 to 1 in both directions. So that's just saving us some time. And then the H value is how high we want the box to be generated off our surface, because surfaces are not three-dimensional solids. They are a surface in 3D space. So here I can set a number in a slider to generate that box off that surface. And I believe you can, if you want it to go the other way, you can put a negative number. So we can make that pop in either direction. That is the box that we want to transform to. So this has the same topology as our bounding box, our original bounding box. So we can plug that into the T value, and this is going to take it, probably the longest. So 1.5 seconds it took for me. It might take you a bit longer depending on what computer you're on. But you can see it's now transformed these cylinders and morphed them onto those surfaces that we've drawn. And you can see here that it's not necessarily capable of taking in those curves, right? So if you've got maybe something that looks like this, that's your tread, then you can use that instead. So I want this to go the other way. Jeez, this is slow. Cool. I reckon that's. Does that make sense? Cool? Yes. Yeah. Yes, what we want to do is we want to explore. You've got this. So, hey, where's your group? Where's the group? Plug that into the group. Oh, jeez. Okay, I don't think I need to record anymore. So let's stop the recording.